Okay, so we're ready to go for really fast spin echo. so I talked last time about our original slow spin echo. That was it was conceptually simple. You just do a 90, wait a certain amount of time, tau, do a 180, wait a certain amount of time, tau, record an echo, and that gave you a nice T2. You could do a nice T2 weighted scan, but it might take like 40 minutes for 6 millimeter thick slices, which is a really long time to wait for somebody in the magnet. So then we talked about turbo spin echo, which was do a 90 and then a 180 and then a string of 180s. So that way we might be able to collect 16 echoes. And so that would potentially go 16 times as fast. But it's still kind of a long time. So still we'll still end up with a, you know, a 20-minute scan or a 15, 20-minute scan. So it's still hard. And remember that you're collecting all this data and assembling it at the end, so any motion that occurs over that entire time could potentially mess up your signal. So and then the other problem is you can't make it's difficult to make very thin slices when you're doing two-dimensional scans. So this is really fast spin echo, which is a 3D sequence. And so I'll draw out sort of the basic 3D FSE, so 3D fast spin echo scan. So 3D FSE. And then I'll finally get up to the really, really fast spin echo, which is the one that we actually use now. How does that one work? But we have to sort of draw out the 3D one first to see how they optimized it. So so if we draw this guy out, what does it look like? It looks like it's got two phase encode. So here's RF in, so we're putting, this is the RF we put in, so we put in our 90, and then we have a 180. So the 90 goes in, and here's our, we select a slice, and then do the slice fixer. And so this was the Z gradient and the Y gradient, and the X gradient. So before we do the 180, when we've got a little time, we're just waiting around, got a little time, then we can do go to the right side of K-space, and then we do our 180. So here's our 180, our first 180. So this is our tau time. And so during this guy, then we have to do, you know, the little crusher and then the little ears on it to sort of, that gets rid of any leftover transfers that we didn't want. And now, since it's a 3D scan, we're going to do a whole series of phase encodes on the, not only on the Z gradient, but also on the Y gradient. So the Y gradient is our normal phase encode direction. And then we'll do, there's a little bit of this guy's a spoiler, so there's like spoilers and crushers. So a spoiler is just getting rid of extra magnetization that we don't want. So here's our little spoiler. So let's label these. So this guy is the partition direction, which is what they call the second phase encode. This is the phase encode direction, gradient direction. This guy's the readout. And then we have to fix, because remember we're recording a whole series of echoes, and so we have to fix the gradient. And so the way that you draw this out is that we go through this set of phase encode steps. So remember what this means is this is like two for loops. So this means, for each partition, and then inside that, for each phase encode direction, do a readout. So there'll be, if there's 64 steps here and 64 steps here, that will be, for 4,096 readouts. So this diagram is a lot of collecting a lot of data. And then if I put the arrow down here, it means like do the opposite of whatever you did there. Because remember, we've got to sort of get everything back in order, because we're going to record more echoes. So if we went up and down in k-space, or in and out, like in the z direction in k-space, just undo it. So this is just undo, and then we're ready to do another one. And so here's another one right here. And we've got to collect a whole bunch of data, so we want to do these as absolutely quickly as possible. So here's the next 180 over here. And then you would have, the immediately do the same thing again. So I'll just draw it out quickly. So immediately do some single combination of partition and phase encode, and then another readout. And then these can be done at the same time as you're doing the spoiler here. So we undo these guys, and then we're ready to go again. So I'll just put a line down here, etc. So, and again, so this guy goes up again, and then we undo whatever we did there, and up again, and undo whatever we did there. So what's the so this is this guy is only first time. So to right k-space. We only have to do it the first time, because the 180 will always flip us to the opposite side. And so what is our signal? So our signal is, there's the big FID, which we're not recording, and then in the middle of this there's an echo, and then in the middle of this there's another echo. But these are falling off pretty quickly. So what we want to do is go as absolutely fast as possible, and what is about the fastest we can go practically? It's about something like 8.5 milliseconds is about the fastest we can go. And so why do we want to go so fast? Well, we've got to fill a three-dimensional k-space. And so so that means we've got to, if we're collecting one by one data, we've got to collect 10 million data points. Or say we're doing a high-resolution scan that's one by one, and so maybe we have 200 partitions and say 200 different phase encodes. So that would be 200 times 200, which is so 200 times 200. So we're going to have 40,000 readouts. So basically, that's why we want to get this as absolutely small as possible. But there's another problem we have, which is that there's all these 180s, and these 180s also stop you from going faster. So we might be able to squish down a little bit, but then we've got so many 180s that we start to overheat the subject. So there's two things that are limiting us. One is too many 180s, and the other one is we've got to do all these slice select pulses. So these things take time. So a reasonably good 180 that selects a slab takes some time. So why did I draw that out if we're doing a 3D scan? Well, it turns out that in practice, with this kind of setup, you can't quite get the whole brain. You can't quite get the whole brain. And the main thing that blocks you is the specific absorption rate, or this is basically the heating of the subject. And so there's a SAR constraint on here. They just call it SAR, meaning like how much you've heated the subject, and you can't heat the subject more than about 1 degree. So an estimate of what the SAR generates, it's proportional to something that involves B0 but squared. So sadly, as you up the B field, like from 1.5 to 3, you deposit more energy, and that's not surprising because energy is equivalent to frequency. So if you look in quantum mechanics, the energy basically is proportional to frequency, and so as you turn the frequency up, you just get proportionally more energy. But it turns out, from the point of view of heating, it's squared. And then the other thing is the flip squared. So whatever the flip angle is also squared. So that's kind of a bad thing, because that means if you double the flip angle, you got 4 times. And then also the width of your pulse, the frequency width of your pulse, is in there too. So if you stimulate more frequencies, you're going to do more heating. So all of these things, and if you do a slice selective pulse with a more narrow range of frequencies, that is better for this term. But you can see there's a problem, and so in practice, a 180 degree is like 4 to 6 times a 90. So the 180s are quite expensive, and so as a result of that, what people have done is they've done something halfway in between slices. So one thing you could do is you could just do slices, 2D slices. So 2D single slices. And at the other end, you could just do a single slab. So we could just do, a single slab. So this is 2D single slices. But you could also just do multiple slabs. So you could sort of select a slab here like that, and then another slab here, say just do 3 slabs, for instance, like that. And you could potentially do those at the same time, So it turns out with this technique, it's hard to collect enough data to get a whole brain in a reasonable amount of time. But potentially what you could do is just record this slab, and then while that one's recovering, then work on this slab, and then work on this slab. So this is called multi-slab. So that seems like a good compromise, but one of the problems is you had to deal with the problem where the slabs overlap, and so there's going to be there's a slice. The slab select pulse is going to be slightly sloppy, and so there's going to be some mess. There's going to be some mess in between the slabs, and there's various things you could do. You could try to make the slabs slightly overlap, and then try to throw away some of the data that was messed up at the edge. There's various tricks, but the end result is you end up with these artifacts going through the image, and so that's kind of a pain, and it might just happen to go right through the part that you wanted to look at, and so So this was developed. This kind of 3D fast spin echo was developed early on, like in the 90s, but it wasn't really heavily used. I used it years ago to scan a dead dolphin brain, and that has the advantage that it doesn't move. So you can scan it for an hour, no problem. It's not going to move, and even if you've got this slab problem, given that it doesn't move, it's going to be a much better scan. But in practice, these scans weren't used very heavily because of the kind of artifacts, and that is now changed with ReallyFast3DSpinEcho. So how could you further optimize this in order to be able to collect a high resolution 3D scan, in just 5 minutes? And that's what we can do now. So several things were done, and so we'll draw this pulse sequence out. So I'm going to draw it out. So let's start off with so this is I put this reading. This is Mugler 2014, if you want to. And what this is, on the Siemens scanner, this is called a space scan. And it was originally developed for rapidly imaging the abdomen, especially with breathing going on in there. But so it was actually just under the abdominal part of the scanner database. But when the human Connectome project started up, somebody looked at that and said, "Hey, you should just use this. It's just like a T2 weighted scan that you can collect in 4 minutes, high resolution T2 scan." And so they started using it for the brain, and so and then it became quite heavily used for the brain. But what we're going to do is just sort of compare several different strategies for getting more echoes. So this is the one that at the end that we'll look at. But we'll start off with, let's just do a whole bunch of 180s. So this is degrees, 0 and 180. So if you just do a bunch of 180s, so this is space 3D fast spin echo. Variable flip. Variable flip. So you can see where we're going. So our standard spin echo, so this is basically standard spin echo. What happens to our signal? Our signal, just falls off like an exponential decay. And so this might be, say, 800 milliseconds over here. 0, so that's milliseconds. So that's signal. This is STD spin echo, fast spin echo. So standard fast spin echo, we just do 180s. And what happens to our signal? This is our, so this is flip series. And this guy is our signal evolution. So that's standard fast spin echo train. Do 180s all along, and then. So what if we just say, let's just do 60s? So 60s, we could easily do a lot more of those. So let's just do 60s. So, what does that do to our signal? So it turns out that actually helps us a little bit. So if I draw that guy in there, so that guy is in there like that, what happens, it doesn't help us at the beginning, But it turns out after a little while, especially for the later echoes, it gives us a little bit of an advantage. Signal doesn't die out quite as quickly because we're not blasting it with so many 180s. And so just the observation of modeling, but what's going on here? Now what's going on here is stimulated echoes. So there's a whole bunch of stimulated echoes going on. So this guy is from above. So why are we getting more? It's from stimulated echoes. So what are stimulated echoes? Well, remember, whenever we did a pulse and then another pulse, then this amount of time afterwards we get a spin echo. But if we do a third pulse, this amount of time afterwards, we get a stimulated echo here. That would occur even if we did evenly spaced pulses. So let me just draw it out there. So if we do an evenly spaced pulse, that's not 180. So that's the critical thing because it's 60. So if we do an evenly spaced pulse, what's going to happen is, so just a train of evenly spaced pulses that are not 180. So what's going to happen is we'll get a, so here's our first one. Sorry, guys. So it's going to be twice as long. So it's this amount twice. That's where the echo is. So that amount. So here's where the echo is. So this guy's a spin echo. But if we do a series of pulses like this, what's going to happen is we're going to get stimulated echoes. So this guy will be a spin echo, but what's going to happen is this thing is going to generate, right at this point, a stimulated echo plus a spin echo plus a stimulated echo. And whether or not we get that stimulated echo is a function of whether or not we did a 180. So if you do a 180, we shouldn't get any stimulated echo because there won't be any kind of saving of transverse magnetization in the longitudinal axis so that it doesn't decay as much. But that's kind of a good thing because it doesn't decay as much. And so that's why this guy is bigger. This guy's bigger because the amplitude of the echo is bigger because this is the signal, yeah. The signal going up like that, degrees going up like that. So it's bigger because of the stimulated echoes. The stimulated echoes decay less rapidly, and so that's why we get more. And so then these authors started just fiddling around with different plans. So what about if we start big, say start big and go to 60? That will kind of smooth this out a little bit more. So here's our original one, which is all 180s. So you get something that sort of looks a little more like that. A little better. But now is the one that they actually use. So let's start really big, or not really big, but pretty big, and then immediately go down quite low. And then so that we don't deposit much heat, and then slowly come up, and then a little extra boost at the end. So what this is the flip. So here's 1 to 180, 0 to 180. So that strange thing, gives you a signal that is much better. So here's the signal that you actually get. So it's got all these stimulated echoes in it. So if you look at our original signal, it's something like that with all the 180s, no stimulated echoes. So now we get something, it starts off pretty high, but not super high, and comes down and stays pretty much the same until right at the end when you're doing this extra little boost. And what happens is we get 10 times the signal here. And so that allows us to do these ridiculously long chains. So this is milliseconds. So you can get an echo out at 800 milliseconds, a whole second. So normally there'd be there's nothing left in a regular spin echo. So basically this is the fact that you've still got some usable signal out here at like 500 milliseconds or 800 milliseconds allows you to collect a lot more lines of K-space. But that relies on the fact that you actually have a way of shrinking your echoes down even more. And so they managed to shrink the echoes down to 3.9 milliseconds. So that's a tiny amount of time. So what the pulse sequence looks like is you do 190. So here's our 190. And so for that, we only have to do this once. So we do a slab select. So that's the slab select. And then, so that's the X gradient, RF in, and Y gradient, and Z gradient. So then what they decided to do, since we're scanning the whole brain, we don't have any sort of multiple slabs to deal with, what we can do is basically do this variable length hard pulse. And so this is our, this is not variable length, variable flip. So because here's the actual flip angle. So variable flip corresponds to this guy here. So depending on where we are in time. So this is time going this way, milliseconds. Forgot to label that. So these are the same x-axis. So it's one of those flips, whatever, wherever we are in time. So now that's just a variable flip hard pulse. So the advantage of that, it's very short. So if you do some kind of slab select pulse, it takes a while to play it out, whereas this takes almost no time. And so then that allows us to do a really super short thing. So this space between these pulses is only 3.9 milliseconds. So that's so that's less than half of the absolute fastest you could go with the original 3D fast spin echo. So since that's a hard pulse, we don't have to do any slice selective pulse because we're just getting the whole brain. We don't care about the whole brain, and we only care about the whole brain. And this thing takes almost no time. And so then all we do is the same thing we did before, which was our two phase encodes, and then our readout. So and then our fix. Oops. Yeah, almost got it. And then our fix phase encodes. So basically, it's just solid wall of data collection, and you can hear this when you run it. It's just like running continuously for a long time. So that's the same pulse sequence as before, except we just took out all the slice select thing. We don't have to mess around with slice select because these are just hard pulses that are stimulating the whole brain. And so if you actually look at the signal down here, what happens is, after this, there's the FID, and then there's a spin echo here. But then, the next time around, this guy is a spin echo. Well, there's a little FID from this guy, right? We're ignoring that also. We're trying to crush it with this. So here's a little FID, then there's a spin echo, and then this guy makes another FID right here, which we also ignore. So this guy's an FID, which we try to crush. Here's the original FID from the 90, which is bigger. And so this guy's a spin echo, and this guy's a spin echo plus stimulated echo. So that's how we do it. And so with this, you can get like a 0.7 millimeter scan in like 6 minutes or something like that. It's 0.7 millimeter isotropic scan because the data collection is going so fast. But that wasn't enough. You had to do this especially optimized sampling of the K-space data. And so the reason I go over this is, again, it's kind of, I've said this a couple times, but what happens is you start off with something like spin echo, very easy to understand. You just do one line of K-space, a 90, 180, collect some data. By the time you sort of get to these really optimized scans, all different kinds of messes are happening. It's not really a standard spin echo. It's got a stimulated echo in it, and you're doing all different kinds of optimizations in order to make it go fast. And it's harder to understand. But if you start with the simple one and then sort of escalate up to this, then sometimes it's better. So let's draw out how we collect the data in K-space. So we've got to collect a cube of K-space, three-dimensional K-space. And I'm going to draw out two different things here. So one is the echo number, because we're collecting these giant long trains of echoes, like 150 echoes. In fact, you can collect a whole plane of K-space just from 190. That's how much data. So you're collecting. So before we said we could do like 30 echo, maybe 15, 16, maybe 30 echoes from 190 in fast spin echo. Here we're doing 150 echoes from a single 90, and that's what makes it possible to actually collect enough data. So, but even that's not enough. You still have to sort of be very tricky about how you collect the K-space data to make it even shorter. And so this is the echo train number. So what I'm plotting out here is like, you have a 90, and then you've got these echoes. An echo train number is, here's one echo train, out to 150. So here's one echo train, and here's another echo train. So where are the different echo trains in K-space? That's the two things I'm plotting out. So we'll first start off with a T2 scan. So the first thing you do is why bother going all the way out in K-space? So let's just throw away this K-space data out here. That will save time. So we just collect like a sphere of K-space instead of, a full cube. That saves another, 5% in time. And then in the center of K-space, let's collect the data very dense. And then outside of K-space, outside of the center, let's collect a little bit less dense. So that saves us some time. We only have to collect really dense data that way. Now, this direction is the readout. So each of these lines here, each of these readout lines is going that direction in K-space. So that direction in K-space is the, the KX direction. KX going that way, so that's the readout. So what we're looking at now, is the how we arrange the partition. This is the partition direction and the phase direction. Here's a readout. So we do this in, if we want a T2 weighted scan, so this guy is long effective TE effective. I'll say what that means for a T2 weighted scan, because we still have to change the contrast. We might want a proton density scan. So so these lines represent sort of like what echo we're on. So this is like echo 5, echo 15, echo 45 or something. Echo 45 we get way out there. So so what is that direction? That direction is the KY direction, and this guy is the KZ direction. But how do we arrange the echo trains? So the echo trains, so here's the center of K-space. It's a little denser, and so now we've got a problem, like we've got to deal with, the fact that there's increased density there. And so the way this works is, so we start here, the left side of K-space, and our first echo sort of goes around like this. But since we've got to record the center more densely, we've got to sort of deviate toward the center. And so here's one of the later echo trains. And then here's an echo train going right through the center. And we want to do that one relatively late, because that's the center of K-space. So here's the center of K-space right there. And that's what controls the contrast. So that guy is done relatively late. And then we sort of like finish up like this. So this might be, so this is train 1, echo train 1. And then this is like echo train 6, and we wait a little while to the 16th echo train to go through the center of K-space. And 26 up there. So this guy would, so this, with all this like special tricky squish the center of K-space, this is basically how we're able to get a T2 weighted scan. But say we wanted a T1 weighted scan, a proton density weighted scan, then what we would do is record the center of K-space early. And so this would be done in a different, so again we throw away the edge of K-space to save time, but collect the center more densely. But then in addition we say just throw away this part of K-space too, because we've got a lot of signal to work with. and just don't even bother collecting a part of K-space. And how could we do that? Well, remember there was this symmetry operation so that we could reconstruct this part of K-space from the data we did collect. And then if we look at, how the echoes are being collected, now they're sort of being collected in circles like that because we want to get a proton density weighted scan. And if we look at the actual sort of echo trains that we're collecting, so here's we're throwing this part away. But now we've still got to collect the center more densely, and so there's a sort of a complicated thing where we collect things, our echo trains sort of come out still somehow covering all of K-space. So we still have to sort of cover all of K-space, but we collect the echoes early. So we start in the center and go out. So here's train 1, 9, 17, 26. So that guy will give us a proton density weighted scan because we're collecting the echo very early before there's been a chance for T2 decay. So this guy is a short TE effective proton density weighted scan. So now the weird thing about this, so one of the things that happens when you look at this and you look at the parameters on the scanner, they don't make sense. And so if we look at, so the time, the time to the center of K-space that's the time from the 90 to the center of K-space. So here's the time from 90 to the center of K-space, which is our time echo effective. So on the scanner, a lot of times they'll specify the time to the center of K-space as the effective echo time because there's, of course, a gazillion echo times. All these different guys are collected at different times. So in this case, like the later points in K-space might be collected like at 500 milliseconds or something like that. But the effective time is what was the time that we collected the center of K-space. So that effective echo time is the one that most controls the contrast. And if this was a regular T2 scan, we would expect, what would we set that effective echo time to? We would set it to something like, say, 100 milliseconds, 60 milliseconds, 100 milliseconds to get a T2 weighted scan because we want time for the signal to, fall off, but then develop contrast, at the very beginning of the scan, there won't be any T2 contrast. So, what will happen is at the beginning of the scan, the things were starting from about the same place, and so you have to wait a while before the contrast builds between the different tissue types. So when you look at a scan like this, the time from the 90 to the center of K-space, the effective echo time is 5 times, what we expect. So in order to get a T2 weighted scan, you can put something like, TE effective equals 500 milliseconds. So that's like 500 milliseconds. That doesn't make any sense because T2 decay at 500 milliseconds you're out here. On a regular T2 decay, 500 milliseconds is out here. There's nothing there. So how could you possibly have a 500 millisecond echo time? But the reason for that is because stimulated echo. And if you look at the stimulated echo equation, it has, a number in there, the basic number in there. There's, e to the minus tau 2. That was when you do a stimulated echo like this. It's this time. So this time is tau 1. This time is tau 2. And remember, you get a stimulated echo over here, STE. So it's tau 1. Tau 1 later, there's a stimulated echo. But if you look at the equation for the stimulated echo, you've got the, e to the minus tau 2 over T1. And so that's a decay that's proportional to T1, but since T1 is like 3 seconds or 4 seconds, this decay is much slower. And so that's why you've got all this signal out here, because you're saving, every time you do one of these little flips, you're saving some of the magnetization in the longitudinal plane, and then that decays. It's still decaying. It's not regrowing. It's decaying. It's decaying at a much slower rate than it would if it was a T2 decay, because T1 is so much longer. So this amount of decay, since this is in the denominator, is much slower. And so, it's because of this thing that, you end up with a T2 weighted scan with a 500 millisecond TE. So, so this is just sort of going through, one of these hyper-optimized scans, but it's very, very useful because you get one of these like a 0.7 millimeter cubed scan in like 5 minutes. It's amazing. So this is ReallyFast3DSpinEcho. So it's called a space scan, or a variable flip angle single slab 3D fast spin echo. And these are widely used now. You would often use them if you collect a T1 scan and then collect a scan like this. You could use this scan to try to do a better job of calculating a quantitative T1. Okay, David, we'll end the recording there, and I'll take a few minutes of questions.